You wake up in the morning, reach for your phone, and notice something familiar. The battery says 82%. Last night, it was 100%. And almost without thinking, you tell yourself, the phone used up some energy. It sounds perfectly reasonable. Your car uses gasoline and moves down the road. You walk for 30 minutes and eventually feel tired. A light bulb turns on and gives off light. A cup of coffee sits on the table and slowly becomes cold. In each case, everyday language gives us the same picture. Something had energy, something used that energy, and now there is less of it. But here's where physics becomes strangely interesting. The word energy feels so ordinary that we rarely stop to ask what we're actually talking about. When your phone battery percentage drops, did energy simply vanish? When gasoline burns inside an engine, where does the energy go? When your muscles become tired, did your body literally run out of energy? And when that coffee cools down, what exactly changed? These questions sound almost too simple, but they lead directly into one of the most important ideas in all of physics. Because physicists use the word energy in a much more precise way than we usually do in everyday conversation. Energy isn't simply a mysterious substance stored inside objects, waiting to be consumed like fuel in a tank. Something much more subtle is happening. The physical system is changing. Energy is being transferred. It can move from one form to another, spread into the surroundings, or become associated with different parts of a system. And once you see that distinction, ordinary events begin to look completely different. Your phone didn't simply eat a substance called energy. So if the energy didn't simply disappear, what exactly happened to it? So where does energy go? That is the question we need to keep in mind. Because if energy cannot simply disappear, then something doesn't quite add up. Batteries die. Fuel tanks become empty. You eat a meal, move your body, and eventually feel tired. A hot object cools down. And every one of these experiences seems to tell us the same story. The energy was there, then it was used up. But that explanation is incomplete. Energy isn't simply destroyed when your phone battery falls from 100% to 20%. It isn't a mysterious fluid that leaks through the universe until nothing is left. And saying, the energy was used, doesn't actually explain anything. It only gives the event a familiar name. Used for what? Transferred where? Changed into what? Those are the questions physics cares about. And here's the strange part. You don't need a particle accelerator, a university laboratory, or advanced mathematics to begin answering them. The evidence is already sitting around you. Look at a battery. Look at the food in your kitchen. Look at sunlight falling through a window. Look at a moving car. Feel the warmth coming from a cup of coffee. These ordinary things are constantly showing you what happens to energy. The clues aren't hidden in some exotic corner of physics. They're right in front of us. But our everyday language tends to compress the whole process into one convenient phrase. Energy gets used up. It's convenient. It's also the reason this subject can become confusing so quickly. Because once you stop imagining energy as something that simply disappears, a much more interesting picture begins to emerge. The question isn't really, where did the energy go? It's, what changed, and where was the energy transferred? And before we go any further, there is a reason this simple question has been explained so badly for so long. There is another reason the word energy causes so much confusion today. You hear people say, raise your energy, protect your energy, manifest with your energy. Feel the energy in the room. And in ordinary conversation, that can be perfectly harmless. People often use words metaphorically because metaphors make complicated feelings easier to describe. The problem begins when the metaphor quietly gets presented as physics. Because then we have to ask a very simple question. What exactly is this energy supposed to be? If energy were literally some invisible substance moving through everything, could you collect it? Could you scoop some out of one object and put it into another? Could you point to its boundary? Could you watch it physically disappear? what would it actually look like? These questions may sound almost childish, but that is precisely why they are useful. A good scientific idea should become clearer when you ask precise questions, not collapse into increasingly vague language. This is one of the habits that made physicists like Richard Feynman so effective at explaining difficult subjects.
Don't hide behind a complicated word. Push the idea until you can say exactly what you mean. And if the metaphor is doing all the work, then you probably don't have an explanation yet. So let's remove one picture from our minds right now. Energy is not a magical, invisible fluid flowing through the universe. It isn't a substance sitting inside your phone, your muscles, or a cup of coffee waiting to be consumed. Physics doesn't require energy to be a material thing at all. Instead, energy is a quantitative property associated with the state of a physical system. That sentence sounds more technical, but the underlying idea is actually simpler. A physical system can have different possible states, and those states can be described by measurable quantities. Energy is one of the quantities we use to describe those states and what can happen when systems interact. That is a very different idea from imagining a mysterious substance called energy hiding inside everything, and it gives us a much stronger way to think. When a battery runs down, we don't have to imagine energy evaporating into nothing. When gasoline burns, we don't need to picture energy being destroyed. When your body becomes tired, we don't have to assume that some invisible fuel tank has simply become empty. Instead, we can ask the questions that actually matter. What physical system changed? What interactions occurred? Where was energy transferred? And once you stop imagining energy as invisible fuel floating around inside objects, the rest of the subject becomes much easier to see. This is the kind of physics we want to explore here, not physics reduced to slogans. Not complicated words used to make simple ideas sound impressive, and not vague explanations that leave you with more mystery than understanding. The goal is to go one level deeper, to take something familiar, ask what is physically happening underneath it, and keep asking questions until the mechanism becomes clear. Because sometimes the most interesting discoveries aren't hidden in exotic equations. They're hiding inside ordinary things you thought you already understood. If you enjoy explanations that focus on how something actually works, rather than simply telling you what to memorize, this is the kind of thinking you'll find throughout the channel. You don't need to be a physicist. You just need to be willing to question an assumption that seems obvious. Now let's follow one simple transformation from beginning to end and watch what the word energy actually means. Imagine a battery connected to a small light-producing device. You switch it on. Something happens immediately, but we need to be careful with the picture in our heads. It is tempting to imagine that the battery contains a supply of invisible energy, and that electrons carry little packages of that energy through the wire into the lamp. That picture is convenient. It is also misleading. 1. Chemical configuration leads to electrical potential. Inside the battery, chemical reactions can change the arrangement of charged particles and molecules. A charged battery is in a chemical state that can drive a process when the circuit is completed. Those chemical processes establish electrical conditions that cause charge to move through the external circuit. The important point is this: the energy isn't a little substance hiding inside each electron. Electrons are physical particles with charge and mass. They participate in electromagnetic interactions. But energy is not another material ingredient attached to them like a tiny backpack. That distinction matters because energy, matter, force, motion, and electricity are not the same thing. They interact with one another, but you cannot simply substitute one word for another. 2. Electrical transfer leads to electromagnetic interaction. Close the circuit, and charge begins moving through the device. The electrical system now transfers energy to components in the circuit. At this point, another everyday picture can become confusing. We often say, the electricity carries the energy. That's acceptable shorthand, but it shouldn't be mistaken for a complete physical explanation. The circuit involves electric and magnetic fields, charged particles, chemical processes inside the battery, and interactions within the device. Energy transfer is a property of the entire physical process. You don't need to imagine a stream of invisible fuel flowing through the wire.
And you can see why the distinction is useful with a simple measurement. Suppose the device operates at 10 watts. A watt is simply a rate of energy transfer. 1 watt equals 1 joule per second.
So a 10-watt device transfers energy at about 10 joules every second while operating. The joule is the SI unit used to measure energy. Already the language becomes more precise. We're no longer saying the electricity is being used. We're describing a measurable rate at which energy is transferred. 3. Electrical transfer leads to light plus thermal energy. Now look at the device itself. Some of the transferred energy can emerge as electromagnetic radiation, the light you can see. Another portion becomes thermal energy associated with the microscopic motion and interactions of particles in the device and its surroundings. This is why a real light-producing device can become warm. And this is where the phrase, "energy gets used up," starts to fail us. The energy didn't simply disappear when the light was produced. The physical system changed. Energy was transferred and redistributed among different forms and parts of the environment. A battery may be losing the chemical state that allowed it to drive the circuit, while the surroundings receive energy through radiation, heating, and other interactions. The accounting continues. 4. What does wasted energy mean? Now consider something engineers call inefficient. Suppose you want a machine to produce useful motion, but a large portion of the input ends up heating the machine. We casually say that energy was wasted. But wasted where? It wasn't destroyed. Usually it means the energy ended up in a form or location that is less useful for the particular job we wanted. That distinction is extremely important. Energy conservation tells us that energy doesn't simply vanish from the properly defined system. Energy transfer describes energy moving between parts of a system or between systems. Energy transformation describes changes in how energy is represented in physical processes. And energy dispersal describes how energy can become spread through many microscopic degrees of freedom, making it much harder to extract for a specific purpose. So when an engineer says, "This machine wastes energy," the statement is usually about usefulness, not destruction. 5. Why does temperature matter? Now imagine that some of the transferred energy ends up making an object warmer. What does warmer actually mean? At the microscopic level, matter contains enormous numbers of particles interacting and moving in complicated ways. Temperature is a macroscopic quantity that tells us about the statistical state of that enormous collection of particles. A hot cup of coffee has a different thermal state from the cooler air surrounding it. Energy tends to be transferred from the warmer coffee to the cooler surroundings. The coffee cools. The surrounding environment receives energy. Eventually, if the system is sufficiently isolated from outside influences, the temperature difference becomes smaller and thermal equilibrium is approached. Again, nothing needs to disappear. The energy has become distributed differently, and this is one reason everyday intuition can be so deceptive. When energy becomes spread among an enormous number of microscopic motions, we don't experience that as a useful burst of energy anymore. We experience it as warmth, or perhaps as an environment that is simply slightly warmer than before. 6. The deeper conservation principle. Now we can finally make the central statement precise. Energy is conserved. But that sentence does not mean that every object keeps exactly the same amount of energy. Your battery can lose energy. The lamp can gain energy. The surrounding air can gain energy. Photons can carry energy away. Different parts of the physical system can change. Conservation means that when we define the relevant system carefully, the total energy accounting balances. If energy decreases in one part, there must be a corresponding increase or transfer elsewhere. That is why physicists don't have to ask, "Where did the energy mysteriously disappear?" They can ask a better question. What changed and where did the energy go within the system? A battery might store energy in a chemical configuration. An electrical circuit can transfer energy. A device can produce electromagnetic radiation. Atoms and molecules can receive thermal energy. And the environment can absorb and redistribute that energy. The chain is continuous. Think about a battery labeled in watt-hours. If it stores, for example, 10 watt-hours, that corresponds to 36,000 joules, because 1 watt-hour equals 3,600 joules.
That number isn't telling you that 36,000 tiny objects called energy are sitting inside the battery. It's quantifying the amount of energy associated with the battery's physical state and its ability to participate in processes that transfer energy. And the same accounting idea scales far beyond batteries. A moving car, a falling object, a heated room, a human body, sunlight striking Earth, all involve physical systems changing and energy being transferred or redistributed. Once you learn to follow that accounting, ordinary events become much less mysterious. But there is still a trap waiting for us. Because if energy is conserved, why do machines become inefficient? Why can't we simply take all that dispersed thermal energy and turn it back into useful work? And this is exactly where the everyday explanation quietly goes wrong. We describe the transformation as consumption. Think about the battery in your phone again. In the morning it says 100%. You use the phone throughout the day. You watch a video. You send messages. The screen lights up. The processor works. The speakers produce sound. By evening, the battery might say 15%, and the natural conclusion is almost automatic. I used up the energy. It feels completely obvious. But now we have enough information to look at the same event differently. The battery didn't contain a little tank of energy that was gradually emptied into the phone. Its chemical state changed. Those chemical processes helped establish electrical conditions in the circuit. Energy was transferred through the electrical system. The phone converted and redistributed that energy through light, sound, electromagnetic radiation, chemical changes, and thermal processes. Eventually, energy was spread through the device and its surroundings in ways that are very different from the original state of the battery. The battery is no longer in the same chemical condition it started in. So when you say, the phone used energy, you're not saying something completely wrong. You're using convenient shorthand. The problem appears when that shorthand creates the wrong physical picture, because used up is not the same thing as gone. And this distinction appears everywhere. Your car uses fuel. Your body uses food. A heater uses electricity. A flashlight uses a battery. An appliance uses power. In every case, ordinary language compresses a complicated physical process into a single verb, use. But physics asks what happened underneath that word. What changed? What interacted? What transferred? What became more distributed? That missing part is rarely included when we first learn the idea of energy. So our default mental model becomes, use energy leads to energy runs out. The more accurate physical picture is, a system changes state to energy is transferred and transformed, to the energy becomes distributed among other parts of the physical world. Nothing about this requires us to abandon everyday language. It simply means we should know when everyday language is being used as shorthand. Because once you mistake the shorthand for the mechanism, the next question becomes unavoidable. If energy is conserved, why does it feel as though useful energy disappears? There is a second misunderstanding waiting just behind the first one. Once you learn that energy is conserved, it is tempting to think, fine, then all the energy must remain available to do useful things. But that doesn't follow. And the reason is that two different questions are being mixed together. The first question is, how much energy is there? The second is, how much of that energy can actually be used to produce the particular change I want? Those are not the same question. You may have learned the phrase, energy can never be destroyed. That statement points toward a genuine conservation law. But as a slogan, it leaves something important out. Consider that cup of coffee again. When it is freshly poured, the coffee is hotter than the room. After an hour, it is cooler. Where did the energy go? It didn't vanish. Energy was transferred from the warmer coffee into the surrounding environment. But now imagine trying to collect all that slightly increased thermal energy from the room and use it to make the coffee spontaneously become hot again. That's a very different problem. The energy still exists. Its distribution has changed. It has become spread among enormous numbers of microscopic degrees of freedom in the coffee, air, table, and surrounding environment. And when energy becomes more dispersed in this way, less of it may be available to produce the specific organized change we want. This is where the second law of thermodynamics enters the story. Entropy is often casually described as disorder, but that word can create more confusion than it removes. A better starting point is to think about how energy and physical states become distributed among microscopic possibilities. Thermodynamics tells us that natural processes have a direction. Thermal energy tends to spread from hotter regions toward cooler ones, and reversing that process requires additional physical intervention. This is why conservation alone cannot tell you whether a process is useful, reversible, or efficient. And the deeper physics goes even further. In modern theoretical physics, Noether's theorem connects conservation of energy with a profound symmetry. The laws of physics do not change merely because we shift the time at which we perform an experiment. That's a remarkable connection. But we don't need advanced mathematics to understand the practical lesson. Energy can be conserved while its usefulness changes dramatically. A battery can power a device. The device can release energy as light and heat. The heat can spread into the room. The total energy accounting still works. But recovering all of that dispersed energy and turning it back into the original useful process is not generally possible without additional changes to the physical system. So the belief we need to update is simple. Conservation does not mean everything remains equally useful. And now we can finally answer the question we postponed at the beginning. What should you actually picture when you hear the word energy? Now we can turn everything we've learned into a simple mental tool. Call it the Feynman energy test. The next time you hear someone say, energy was used, energy disappeared, or even energy flowed into something, don't immediately accept or reject the statement. Run 5 questions. Step 1. What is the system? First, identify what you're actually talking about. Is it a battery, a car and its fuel, a falling object, a light bulb, a cup of coffee in the surrounding room? Energy doesn't need to be discussed as if it exists independently of physical things. Start with the physical system. Step 2. What changed? Now identify the physical change. Did something accelerate? Did an object move to a different position? Did its temperature change? Did its chemical configuration change? Did its electromagnetic state change? Don't worry about using perfect terminology yet. Just find the physical event. Step 3. Where did the energy come from? Now trace the source. If a lamp becomes bright, what physical system supplied the energy? If a ball accelerates downward, what is changing in the gravitational system? If a battery powers a device, what process inside the battery makes the transfer possible? This question forces you to replace vague language with an actual chain of physical events. Step 4. Where did it go? Follow the transformation. Maybe some energy becomes motion, some becomes electromagnetic radiation, some becomes thermal energy, some may become sound, some may be associated with chemical changes or deformation. The point isn't to force every event into one particular category. The point is to follow the accounting instead of stopping at the phrase, "it was used." Step 5. Did I accidentally imagine energy as a substance? This is the most important checkpoint. If your explanation requires energy to behave like a liquid that can be scooped up, poured somewhere else, or simply disappear, stop. Ask what physical quantity or process you are actually describing. That doesn't mean every statement using words like flow is automatically wrong. Physics uses useful mathematical and conceptual language involving energy transfer and flow. The danger is confusing that language with a literal material substance. Now test the framework. Your phone battery? Its chemical state changes, energy is transferred through the electrical system, and the device redistributes that energy into different physical processes. A gasoline engine? Chemical energy associated with the fuel participates in reactions, while energy is transferred into motion, thermal energy, radiation, and other forms. A person eating food? Here we need to be precise. Biological organisms really do perform biochemical energy transformations. Chemical energy associated with nutrients participates in metabolic reactions and ultimately supports processes such as movement, maintaining temperature, and cellular activity. That's real physics and chemistry, not vague human energy. A falling object? Its position changes within a gravitational system, and energy associated with that configuration can be transformed into kinetic energy and eventually other forms. A light bulb? Electrical energy is transferred into electromagnetic radiation and thermal processes. And your cooling coffee? Energy moves from the warmer coffee into the cooler surroundings. 6 ordinary situations, 1 mental framework. And now return to that ordinary object we started with, because it looks completely different once you stop imagining energy as something that simply disappears. The phone is still sitting on the kitchen table. The battery percentage is lower than it was last night. But now you can see what that percentage really represents. The battery didn't simply lose a mysterious substance called energy. Its internal chemical state changed. Energy was transferred through the electrical system, transformed through the phone's components, and ultimately distributed among different physical processes and the surrounding environment. And tomorrow, you'll probably do it again. Then the next day, potentially 365 times a year. But now, every time you see that battery percentage fall, you have a better question. What changed, and where did the energy go? And once you begin seeing energy this way, ordinary physics becomes much harder to misunderstand. The goal isn't to memorize more scientific vocabulary. It's to become better at questioning the words you already use. Because energy, force, time, space, and even matter can sound obvious until you ask what they actually mean physically. That habit of asking one more question can turn an ordinary object into a fascinating physics lesson. If this kind of mechanism-first explanation is useful to you, consider staying with the channel for more. Because sometimes the most interesting mysteries aren't hidden somewhere far away. They're hiding inside the words we think we already understand.